whenever, imagine if they are identical mass, okay, of okay, then the equation of motion must be written to describe the angular rotation. Okay, so you then going to have moment inertia times angular acceleration is then equal to the moment about the pivot. Okay, why we cannot write this? You can no more writing this tangential force anymore, because the tangential acceleration for this is positive here, and then the tangential acceleration here is negative. Okay, so they're different in direction. You cannot do the sum of the tangential acceleration. What you can do is the sum of the moment of inertia and angular acceleration. If now I change the question a little bit to be different from your experiment, just to distinguish the effect. If this is L away from the pivot, but this is 2L away from the pivot, what you first have to determine is your J naught, moment inertia. Moment inertia can be obtained from your kinetic energy. What is your kinetic energy? Kinetic energy for this case is the apple mass, red one times the tangential velocity. Okay, this for the red apple. And what is the kinetic energy for the green apple? Okay. So together you have written it half, and then this one is going to be written as theta dot square, and then this one is going to be 4 times ml square plus ml square. So altogether equal to 5 times ml square. Okay? So half J naught. Okay? Omega theta dot is then your kinetic energy. So in this case, your J naught is 5 times ml squared. Okay? And what about the moment? The moment acting on this, okay, can be simplified. Okay, because now the weight is pointed down, but because relative to the pivot, okay, the red apple is having a moment being clockwise. Okay, how much is that? Okay, you can simply write that this is your moment. Okay, imagine you take the tangential component mg sin theta. This moment coming from the red apple is mg sin theta. Clockwise moment is negative because I define it from the clockwise angle, and then times 2m. How about the green apple? The green apple at the top, okay, will have the tangential component of its weight mg sin theta pointed to cause a counterclockwise moment mgl sin theta. Okay, so we obtain moment inertia from the previous equation, and then next we find out the moment Okay, the green apple is causing a positive moment, which is counterclockwise. The red apple is causing clockwise moment. And the sum of the moment is negative, meaning it is counterclockwise. And finally, upon substitution to the equations, you have phi ml squared theta double dot equal to minus mgl theta. And upon the solution, you can find the natural frequency. This time round, okay, you can see that how do you write the equation, how do you write the frequency equation. Okay, you have the equation being phi ml squared double dot plus mgl theta equal to 0. This is a coefficient for the second order derivative, and this is a coefficient for the third zero order derivative. Your natural frequency can be simply written as coefficient for the zero order derivative divided by coefficient of the second order derivative. Okay, in this way, you can find your natural frequency to be G over phi L. Okay? Previously, we learned about the simple pendulum. We have the natural frequency being square root of G over L. But here we prove that if you now have the double echo pendulum, the natural frequency, okay, is square root of G over L divided by phi. So meaning the natural frequency is going to be lower than the simple single echo pendulum. Okay, in that way, yeah. So that proves the duality of the derivation. Okay, and okay, tomorrow then we'll continue with the compound pendulum. Finish the experiment. Okay, 好，今天就上到这里，再见。